Alright, in this video, I'll be solving my CIE A-Level Maths 9709 Pure 3 May June 2025 guest paper. If you want a PDF copy of this paper, that will be the first link in the description down below. If you're feeling anxious, overwhelmed, or unsure where to start, then I've created a complete course that streamlines everything with step-by-step videos, interactive quizzes, and an exclusive student community to keep you on track. You can get access to it by clicking the first link in the description. Otherwise, like the video, subscribe, and let's dive right in. Number 1. On a sketch of an Argand diagram, shade the region whose points represent complex numbers z satisfying inequalities. The modulus of z minus 3 minus 4i is less than 2, and argz is greater than or equal to a quarter pi. So let's draw our complex plane. We're going to have our vertical axis, which is the imaginary axis. And then we're going to have our real axis. Okay, so we'll start with this first inequality. So that's z minus 3 minus 4i, and this is less than 2. We know that if we have anything of the form z minus a, where we're saying a is a complex number, and this is equal to k, this is going to be a circle where a is the center, and then k is the radius. So what this means in our case is, first of all, we have to factor out a negative sign. We have to be able to clearly see that negative sign. So we're looking at z minus, and then that's 3 plus 4i. So a complex number here is 3 plus 4i. This is less than 2. So we've got a circle, and our center is going to be 3, 4i, and our radius is 2. So that's what we need to draw. So it's 3 units in the real axis, so 1, 2, and 3. And then 4 units in the imaginary axis, so I, that's 2i, then 3i, so 4i should be here. So the center of our circle is going to be somewhere here. And we know that our circle has a radius of 2. So let's draw our circle. Alright, I think that looks decent. Let me just shift it that way. Yes, this is going to be our circle. Make sure that it's somewhat accurate. But notice, because our sign here says less than 2, it means we want the points that are inside the circle, right? And so it means we are not including any of the points on the circumference. If it was less than or equal to, then we would include the points on the circumference. So instead of having a solid line here, we're going to need to have a dashed line. So I'm just going to trace over so that we've got a dashed circle, and then I'll remove the solid line. Okay. So the points that satisfy this inequality would be the points that are inside this circle. But I'll just unshade that for a moment, because we also need to consider the second inequality. Argz is greater than or equal to a quarter pi. So you're going to take your protractor, and then you want to open an angle of 45 degrees, because we've got a quarter pi. Remember to convert to degrees, it's going to be 180 over pi. So that cancels out, and 180 over 4 is 45 degrees. So you want to open up an angle of 45 degrees, starting from your origin here. So if we open up, let me put that in green. If we open up an angle 45 degrees, it should look something like this. All right. So this here would be, that is a quarter pi. And we want the points that are above this green line, because that would be greater than a quarter pi. And we can keep our green line solid because we're saying greater than or equal to a quarter pi. So putting both regions together, we want the points inside the red circle and above the green line. So that's going to be this region over here, or these points. That would be our Argand diagram. Number 2, the variables x and y satisfy the equation x to the power k is equal to y over a, where a and k are constants. The graph of ln y against ln x is a straight line passing through the points 0.501.24 and 1.01, 1.91 as shown in the diagram. Find the values of a and k, give each value correct to 2 decimal places. This is linear law. We have to reduce this relationship that we have to a linear form so that we can find the equation of this straight line that we have over here. Remember that we can write the equation of any straight line in the form y equals mx plus c. So if they're saying that they've got a line of ln y against ln x and that is a straight line, we should be able to write it in this form. Since they're saying x and y satisfy this equation x to the k is equal to y over a, we should be able to reduce this equation that we have to a form that looks like y equals mx plus c. Alright, so the way we're going to do that is to apply the natural logarithm on both sides so that it's ln x to the k is equal to ln y over a, and then we're going to use our laws of logarithms to bring down the power here so that it's k ln x, and then here again we're going to use our laws of logarithms so that becomes ln y minus ln a. Okay, and because we're trying to get to the form y equals mx plus c, I'm going to make ln y subject of the formula. So it's going to be ln y is equal to k ln x, and then move this negative ln a to the other side. It becomes positive ln a. Okay, so they are saying that they've got a straight line in ln y against ln x. So let's compare that to the general equation of a straight line, y equals mx plus c. All right, so ln y in this case represents y, and then ln x in this case represents x. So that should mean this k here represents our gradient m, and then this ln a represents our y-intercept c. So we can use this information to help us find what k and a are. So we can start off with k. We know that k is going to be the same as the gradient m, so m is equal to k. So if we can find the gradient m, we can use that gradient to find k, or essentially that gradient is going to be k. Since we have been given 2 points that lie on the line, we can use y2 minus y1 over x2 minus x1 to get our gradient. So m is going to be equal to, that's 1.91 minus our 1.24, and this is over 1.01 minus our 0.50. And so our gradient m is, let's punch this into the calculator, that's 1.91 minus 1.24 over 1.01 minus 0.50, and that is 67 over 51. So since we said m is equal to k, it means k is 67 over 51. And they want the answer to 2 decimal places, so k would be, that would be 1.31 for k. Okay, now that we have k, we also need to find a. Now the way we're going to find a is, we know that ln a represents the y-intercept c. So we're going to approach this in essentially the same way that you would when you are looking for the y-intercept. You're going to use your gradient m as well as one set of coordinates for a point that lies on that line. So for example, we could say that our set of coordinates is our 0.50, 1.24. But be very careful with how you substitute your coordinates here, because remember that this first coordinate is going to be in terms of ln x, and then this second coordinate is going to be in terms of ln y. So when you're substituting, you're replacing ln x with 0.50 and ln y with 1.24. Right. So coming back to our equation of our line, so if we substitute, ln y is going to be replaced by 1.24, and this is equal to k. Use the exact value here because we don't want any rounding errors. 67 over 51 times ln x. Our ln x is going to be 0.50 plus our ln a. Okay. So we get that ln a is going to be equal to, that's 1.24 minus our 67 over 51 times 0.5. So ln a is equal to, let's punch this into the calculator, that's 1.24 minus 67 over 51 times 0.5, which gives us 14872550. And so to find a, we need to take the exponent on both sides. So here it would cancel out and you get a is equal to the exponent of 1487 over 2550. So let's evaluate that. We get 1.79165 and so on. We need to give our answer to 2 decimal places. So a is going to be 1.79 and k, we concluded, was 1.31. So that's how we find a and k. Number 3, use the substitution root 3x is equal to tan theta to find the exact value of the integral from 0 to 1 of 1 over 1 plus 3x squared with respect to x. Give your answer in the form a plus b pi, where a is rational and b is irrational. So we've got the integral from 0 to 1 of 1 over 1 plus 3x squared, and this is with respect to x. And we're given the substitution root 3x is equal to tan theta. So what we need to do first of all is to use the substitution. So it means we have to replace all the x's with theta. So I'll start with our limits. We want to move our limits from x to theta. So the way that we're going to do that is to say that theta is going to be arctan of root 3x. And I'll start with our lower limit at x is 0. We're saying theta is going to be arctan of 0, which is just 0. And then at x is 1, our upper limit, this is going to be theta is arctan of root 3 times 1, so just root 3. And so theta is, we punch this into the calculator, we get a third pi. So it means our new limits here are going to be from 0 to a third pi. And this is 1 over 1 plus 3x squared with respect to x. So that's our limits done. The next thing you want to do is to differentiate your substitution. So we've got root 3x is equal to tan theta. So we are going to differentiate this implicitly. Alright, so differentiate root 3x, you're going to get root 3. And then if you differentiate tan theta, you're going to get sec squared theta. But remember, we're differentiating with respect to x, so this is going to be d theta dx. Okay, so be careful with that. One way to think about this is that essentially what you are differentiating is y is equal to arctan of x. If you wanted to differentiate this, you would take tan on both sides. So tan y is equal to tan of arctan of x. All right. So the tan and arctan would cancel out so that you've got tan y is equal to x. And this you differentiate implicitly because we don't know how to differentiate arctan directly. So we have to rewrite it in terms of tan so that we can differentiate it implicitly. And here, if you did that with respect to x, it would be sec squared y dy dx is equal to 1, which is pretty much what we have here, except we are dealing with theta. And so now the goal is for us to make dx subject of the formula because we want to get rid of the dx. So it means dx is equal to sec squared d theta. And this is over, we're moving the root 3 down here. So root 3. So we can now come back here and say we're integrating from 0 to a third pi, and we've got 1 over 1 plus 3x squared, and this is squared. Replace the dx with sec squared theta d theta over root 3. So sec squared theta d theta over root 3. Okay. And the 1 over root 3, we can just take it outside the integral sign because that's a constant. Right. So that would be 1 over root 3. And now we have to replace this x or rewrite it in terms of theta. So to do that, we're going to use our substitution, which says root 3x is equal to tan theta. And we want to replace, here it would be best to just replace the whole of x squared. So if we can make x squared subject of the formula in this equation, then we'll be able to replace it. So to do that, we have to square both sides. So when you square, be careful here, root 3 squared will be 3 and then x squared. And this is going to be equal to, that's tan squared theta. Or in fact, we can replace the whole of 3x squared because here we've got 3x squared is tan squared theta. So you can come here and remove the 3x squared theta, replace it with tan squared theta. So it's 1 over root 3, the integral from 0 to a third pi. And this is 1 over 1. We're replacing our 3x squared with tan squared theta. So it's 1 plus tan squared theta, and this is squared times our sec squared theta d theta. And since here we've got sec squared theta in our numerator, we could also rewrite tan squared theta in terms of sec squared theta because we have an identity that allows us to do that. We know that 1 plus tan squared theta is identical to sec squared theta. So we can say that tan squared theta is sec squared theta minus 1. So we can replace this tan squared theta with sec squared theta minus 1. So that what we have here is 1 over root 3, the integral from 0 to a third pi of 1 over, this is 1 plus, and we're replacing our tan squared theta with sec squared theta minus 1. So plus sec squared theta minus 1, and this is squared times sec squared theta d theta. Notice how 1 and minus 1 cancel out, so that what we end up with is 1 over root 3, the integral from 0 to a third pi, and now it's just 1 over sec squared theta squared. Okay, so I'll keep it like that, sec squared theta squared, and this is times sec squared theta d theta. So we can cancel out sec squared theta and the power 2 here on the denominator. And so now what remains is 1 over root 3, the integral from 0 to a third pi, and this is 1 over sec squared theta d theta. Remember that sec squared theta is just 1 over cos squared theta. So what we have is the integral, or 1 over root 3, the integral from 0 to a third pi of 1 over sec squared theta, which is 1 over cos squared theta. So this will simply just be cos squared theta with respect to theta. So this is what we're integrating, cos squared theta. And so now we have completely substituted. We've used our substitution to move from x to theta. So now we have to integrate. But remember that we can't integrate cos squared theta directly. To do that, we have to use an identity, and we use the double angle formula for cos. So cos 2 theta is identical to 2 cos squared theta minus 1. And we want to rewrite our cos squared theta in terms of cos 2 theta. So we have to make this cos squared theta subject of the formula. So that's 2 cos squared theta is equal to, that's 1 plus cos 2 theta. And so cos squared theta is equal to, divide both sides by 2 or multiply by half. Okay. And so we can replace this cos squared theta with half times 1 plus cos 2 theta. So what we now have is 1 over root 3, the integral from 0 to a third pi of, that's half times 1 plus cos 2 theta d theta. And I'm just going to take this half outside the integral sign, so it becomes 1 over 2 times root 3, so 1 over 2 root 3. And we're integrating from 0 to a third pi, and it's 1 plus cos 2 theta. And now we can go ahead and integrate. So that's 1 over 2 root 3, and if you integrate 1 with respect to theta, you get theta, plus if you integrate cos 2 theta, you're going to get sine 2 theta. Differentiate the 2 theta, you get a 2, and so that means we have to divide by 2. All right, and our limits are from 0 to a third pi. So we can go ahead and substitute in our limits. 1 over 2 root 3, and then the upper limit is going to be a third pi plus half sine 2 times a third pi. And for the lower limit, it looks like if we substitute 0 here, it will just be 0, and then sine 0 is 0. So we can ignore the lower limit in this case. All right, so we've got 1 over 2 root 3 times 1 over 3 pi, and then that's half sine of 2/3 pi. Okay, that gives us positive root 3 over 4. So let's just fully expand this. So we've got our 1 over 3 times 1 over 2 root 3, and this gives us root 3 over 18 pi. And then this times that, so that's 1 over 2 root 3 multiplied by root 3 over 4, which gives us, that's positive 1 over 8. And this is going to be our final answer. Let's just check that we have it in the form that they wanted in. They said a plus b pi. Okay, we have that. B, okay, so the number multiplying b must be irrational. Oh, the number multiplying pi. So this is in fact irrational, and this is rational. So yes, that would be our final answer. It satisfies their requirements. Number 4, the equation of a curve is y e to the 2x minus y squared e to the x is equal to 6. Find the gradient of the curve at the point where y is equal to 2. So notice that we've got an implicit function here, so we have to differentiate implicitly. It is implicit because it is very difficult for us to make y the subject of the formula or x the subject of the formula. So we're forced to differentiate it implicitly. So that's y e to the 2x minus y squared e to the x equals 6. Once we differentiate our function, we're going to get dy dx, and then that's going to be the gradient, right? But we want to find the gradient at y equals 2. So we have to then substitute in y equals 2. All right, so let's differentiate. Let's start with the first term, y e to the 2x. So this is a product of two functions, so we use the product rule. And a neat way to think of the product rule is that you just hold the first function, so hold y, then differentiate e to the 2x. So that's going to be 2e to the 2x. Then now you're going to hold the second function, e to the 2x, and then differentiate the first function. So differentiate y. You differentiate y, you get dy dx. All right, and again here we've got another product. So hold the negative y squared, differentiate e to the x, you get e to the x. Now let's hold the e to the x, differentiate negative y squared. So that's going to be negative 2y dy dx. And then here we've got a constant. You differentiate a constant, you get 0. All right, so let's simplify. Here that is 2y to the 2x. Then we've got plus e to the 2x dy dx. And minus y squared e to the x minus, be careful here with the signs, 2y to the x dy dx, and this is equal to 0. All right, so now we want to make dy dx the subject of the formula so that we've got our gradient function. So it means move everything that does not have dy dx to the right hand side. So we're going to keep this term and this term on the left. So that's e to the 2x dy dx minus 2y to the x dy dx, and this is equal to, that's going to be this term. When it moves to the right, it becomes positive, so y squared e to the x, and this becomes negative, so minus 2y to the 2x. Okay, so since we want to make dy dx subject of the formula, let's factor out our dy dx. So that's dy dx times e to the 2x minus 2y to the x, and this is equal to y squared e to the x minus 2y to the 2x. And now divide both sides by this bracket here. So dy dx is equal to, that is y squared e to the x minus 2y to the 2x over, that's e to the 2x minus 2y to the x. And it looks to me that every term in our fraction here has an e to the x. So we should be able to factor out e to the x. Okay, just so that we've got a simplified expression. So in the numerator, if you factor out e to the x, that's y squared minus 2y to the x. And then in the denominator, if you factor out e to the x, that is e to the x minus 2y. So it would then end up cancelling out, so that our dy dx is equal to y squared minus 2y to the x, and this is over e to the x minus 2y. Okay, but remember that we want to find the gradient at y is equal to 2. So we have to substitute in y is equal to 2. But the problem is our gradient also has x, right? So even if we substitute y with 2, we still need to figure out what x is when y is 2. So to do that, we have to use our original function here. We're going to substitute y with 2 into this equation so that we can figure out what x is when y is 2. So I'm going to do that in red here. So replace y with 2. So that's going to be 2e to the 2x minus y squared. So 2 squared, and that's e to the x equals 6. So you get 2e to the 2x minus 4e to the x. I'll bring the 6 to the left, so minus 6 is equal to 0. Divide through by 2. So that's e to the 2x minus 2e to the x minus 3 equals to 0. Notice how this is a quadratic in e to the x, right? Because you can write this as e to the x squared minus 2e to the x minus 3 is equal to 0. So we can solve our quadratic, and here it's a nice one. We can factorize this quadratic. Alright, so we want factors of negative 3 that add up to negative 2. So that's going to be negative 3 plus 1. All right, so either e to the x is 3 or e to the x is -1. We know that the exponential function y equals e to the x doesn't exist below the x-axis. Or another way of seeing it clearly is to just take the natural logarithm here, right? On both sides. So ln, you'd get x is ln -1, which is going to give you an error because that doesn't work. So it means that we've got e to the x is equal to 3. So let's just bring that down here and finish solving it. We've got e to the x is equal to 3. So we take the natural logarithm on both sides. The ln and the e cancel out. So you've got x is ln 3. So we now know that when y is 2, x is ln 3. So we can use this information to find our gradient at y is 2. So let's simply substitute into our gradient function dy dx. So that's going to be y squared, which is 2 squared, minus 2 times y, which is 2, e to the x, so e to the ln 3, and this is over e to the x, so e to the ln 3, minus 2 times y, so 2 times 2. Okay, and then here we've got 2 squared, so that's 4, minus 2 times 2, that's 4. E and ln cancel out, so you just remain with a 3 there, over e and ln cancel out, so you've got a 3 there, and then minus 4. Right, so this leads to, that's 4 minus 12, which is minus 8, over 3 minus 4 minus 1, so we get 8. So therefore our gradient is 8 when y is 2. And that will be our final answer. Number 5, part A. By sketching a pair of suitable graphs, show that the equation cot x is equal to 2 plus sine x has exactly one root denoted by a, and the interval x is between 0 and half pi. Okay. So the two graphs you have to draw would be y is equal to the left hand side, so cot x, and y is equal to the right hand side, y is equal to 2 plus sine x. And our sketch should show that there is only one point of intersection, because that would mean that we have exactly one root. Alright, so I'm going to draw our Cartesian plane. This is the y, and then this will be the x. We are going up to half pi. So let's start with y equals cot x. What we are looking at is we've got an asymptote at 180. So let's put pi somewhere here, and then 2 pi should be somewhere. So we've got an asymptote at 180, which is pi, and another one at 2 pi. Oh man, that asymptote is not straight. But I hope you get the idea. So this would be pi over 2. This is 3 pi over 2. So it's going to look like this. And then on this end, it's also going to look exactly the same. But we are just interested up to half pi. So this is the part that we want. So we have to draw that here. Our x's are a bit small. I think maybe let's move our y-axis downwards a bit. I think let's move our y-axis a bit downwards so that we've got more room to go up, right? So our y equals cot x, we say it is going to look like this. Like that. This is y is equal to cot x. And then we also have to do y equals 2 plus sine x. So let me just move this to the side so that we can see how we get y equals 2 plus sine x. We know that the graph of y is equal to sine x looks like this, right? This is y equals sine x. Let me label x's. This would be pi. This is 2 pi. So x, this is our y. And this here would be 1. This is -1. Okay, perfect. All right, so there's this 2 now that has been added to y equals sine x. So that means we have to shift our graph upwards by 2 units. So y is 2 would be there. So you're just shifting your curve upwards in the y-axis by 2 units. So it comes right there. And notice we are going up to half pi. So half pi would probably be somewhere here. So 1/2 pi. Okay. So let's assume that our 2 is somewhere here. It means we only want this part here. That's what we're looking at. And I'll put that in green. So it's going to look like this right there. And this is y is equal to 2 plus sine x. And hopefully you can see that they will only have one point of intersection, which means that they have exactly one root in this interval. And then part B says verify by calculation that A lies between 0.2 and 0.6. Okay, so in part A, we were given that cot x is equal to 2 plus sine x. And this equation has the root that's being denoted by A. And we need to show that A lies between 0.2 and 0.6. So we're going to create a function if that's defined by f of x is equal to, we're going to take the 2 plus sine x and move it to the left. So it's going to be cot x minus 2 minus sine x. And if a lies between 0.2 and 0.6, it means that when we evaluate f of 0.2 and f of 0.6, we're going to get a sign change. So we can start by evaluating f of 0.2. Remember that cot x is just 1/tan x. If you don't have cot on your calculator, you can use 1/tan. So that's minus 2 minus sine 0.2. Let's punch this into the calculator. Make sure you're in radians. That's 1/tan 0.2 minus 2 minus sine 0.2. And this gives us a positive 2.73 and so on. And let's evaluate f of 0.6. So that's going to be 1/tan of 0.6 minus, that's 2 minus sine 0.6 is equal to, so that's 1/tan 0.6 minus 2 minus sine 0.6, and here we get negative 1.10 and so on. So as you can see, we've got a sign change, right? It was positive for 0.2 and now it's negative for 0.6. So we can conclude that, therefore, since there is a sign change, a root, or in fact the root a, because they've named their root as a, the root a lies between 0.2 and 0.6, 0.2 and 0.6, and this would be our final answer. This conclusion is important to get the second mark for this question. They want to see that argument or that conclusion that we've got a sign change, so our root must lie between these two values. Part C says, show that if a sequence of values in the interval x is between 0 and half pi given by the iterative formula xn plus 1 is equal to arctan of 1/2 plus sine xn converges, then it converges to A. This is just a fancy way of trying to say that, show that this equation is the same as the equation in part A. This cot x is equal to 2 plus sine x. Because what they are saying is, remember this iterative formula, you would carry out your iterations using your iterative formula, then when it converges, it means that you have found your root. So they're saying that show that this root that you get when it converges is the same root as the one from part A. And the only way for those roots to be the same means that this has to be exactly the same equation as the one in part A, just written in a slightly different way. So we're going to have to show that this equation is the same as, what is our equation? Cot x is equal to 2 plus sine x. So cot x is equal to 2 plus sine x. All right, so remove the n plus 1, remove the n, you've got x is equal to arctan of 1 over 2 plus sine x. And now we have to find a way to get back to cot x is equal to 2 plus sine x. So for starters, what we could do is we want to apply tan on both sides, right? So we want to say tan x, tan of arctan. And so here the tan and arctan would cancel out so that you've got tan x is equal to 1 over 2 plus sine x. All right, and we need to get cot. Remember, cot is just 1 over tan x. So it means we can just swap these two, right? So if we did it the long way, this would be multiply both sides by 2 plus sine x. So 2 plus sine x tan x is equal to 1. Then now divide both sides by tan x. So you get 2 plus sine x is equal to, that's 1 over tan x. And we said 1 over tan x is cot x. So we get cot x is equal to 2 plus sine x. And so we've proved that this iterative formula is the same as the equation in part A. So it means the root when the iterative formula converges is the same root that you get in the equation in part A. So part D says use this iterative formula to determine A correct to 2 decimal places. Give the result of each iteration correct to 4 decimal places. All right, so we've got our iterative formula xn plus 1 is equal to arctan of 1 over 2 plus sine xn. Okay, we need an initial value that I'll call x0. We know that our root must lie between 0.2 and 0.6. So I'm going to just use 0.2 as our initial value. All right, so x0 is 0.2. So that means x1 is going to be arctan of, that's 1 over 2 plus sine. It's going to be sine of x0, so sine of 0.2. Punch this into the calculator. This is arctan of 1 over 2 plus sine 0.2. And this gives us, that is 0.4269. Remember they said give the result of each iteration to 4 decimal places. So x2 is going to be arctan of, now instead of having to manually punch the result of the previous iteration into your next calculation, we can just use the answer function on the calculator. So find the button written ANS on your calculator and just replace the 0.2 with ANS. Okay, and so what this ANS button does is that it stores the result of the previous calculation. So now you don't have to keep manually punching in the result of the previous iteration. So you just have to simply press equals. Once you've substituted with ANS, press equals, you get the result of your next iteration. So I get 0.3927. And again, don't change anything, simply press equals. I get 0.3974. It hasn't converged yet. X4, press equals. That's 0.3967. It looks like we have converged. This is 0.40 to 2 decimal places, right? So as soon as you get 2 consecutive iterations with the same value correct to the specified degree of accuracy, it means that your sequence has converged, and that's going to be your root. So we can conclude that therefore A is 0.40, and that will be our final answer. Number 6, find the complex number z satisfying the equation z minus 2i over z plus 2i is equal to 21 minus 12i over 13. Give your answer in the form x plus iy, where x and y are real. Alright, so we've got z minus 2i over z plus 2i, and this is equal to 21 minus 12i over 13. Right, for starters, let's use cross multiply. So we've got 13 times z minus 2i should be equal to 21 minus 12i multiplied by z plus 2i. Now we know that z should be in the form x plus iy, so we can say let z be x plus iy, and then we're going to substitute our z with x plus iy. So we've got 13 times x plus iy minus our 2i, and this is equal to 21 minus 12i times z, which is x plus iy plus our 2i. So that's 13. Here we're going to have x, and then we can factor out the I in those two terms, so that it's y minus 2i. All right, and this is equal to 21 minus 12i times x, and we're going to do the same thing. We want to factor out I, so that's y plus 2i. And now we can expand our brackets. So we've got 13 times x, that's 13x, and then 13 times this bracket, so plus 13y minus 2i. We might expand that further in the future if we have to, but for now, let's just keep it like this and see where this goes. And then here, 21 times x, so 21x, then 21 times the bracket, so plus 21, y plus 2i, and then negative 12i times x, so negative 12xi, and then negative 12i times the bracket, so that's negative 12i times y plus 2i. All right, so we've got 13x plus our 13y minus 2i is equal to 21x plus our, I think I'm going to multiply the 21 inside this bracket here, so that is 21y plus 42, and we've got I minus our 12xi. And then here, notice that this part, let's do it on the side. We've got negative 12i times y plus 2i. So it's going to be negative 12y plus 2. And we've got I times I, which is I squared. Remember, I squared is equal to negative 1. So this just ends up being negative 12 times y plus 2 multiplied by negative 1. So that is positive 12 times y plus 2. So if we expand, it's 12y plus 24. All right, so we should have plus 12y plus 24. So on the left, we've got 13x plus 13 times y minus 2 times I is equal to. Then here, I want to put the real parts together. So we've got 21x, that's real. We've got 12y, that's also real. 24, that's also real. All right, and then our imaginary parts, we want to put them together as well. So we've got 21y plus 42, and if we factor out I from both these terms, the negative 12x also moves inside the bracket. So it's negative 12x, and that's I. So now we can clearly see the real and imaginary parts on both sides. So on the left, the real part is going to be this 13x, because that's the only term without an I. And then on the right, the real part is going to be all these three terms, because they don't have I. So two complex numbers are only equal if and only if their real parts are equal as well as their imaginary parts are equal. So in this case, since we're saying that these two sides should be equal, it means that the real parts 13x should be equal, that's 21x, 21x plus 12y plus 24. The real parts should be equal, and the imaginary parts should also be equal. So it means that we also get that 13 times y minus 2 should be equal to our bracket here, 21y plus 42 minus 12x. You can omit the I since they appear on both sides, so they would cancel out anyways. So what we'd end up with are two equations in terms of x and y that we could solve simultaneously. So here I think we can let's make y the subject of the formula in this equation. So that will be 12y is equal to 13x minus 21x minus 24. So 12y is equal to 13x minus 21x, that's negative 8x minus 24. Divide through by 12, you should get that y is equal to, that is negative 2/3 of x, and then we've got negative 2. Alright, so we can substitute y in this equation. I think let's first simplify that equation, because we can simplify. So if we expand on the left here, it's 13y minus 26 is equal to 21y plus 42 minus 12x. Okay, so we can move this 21y to the left, so that is 13y minus 21y is equal to, and then move the negative 26 to the right hand side, so it's 26 plus 42 minus 12x. So 13y minus 21y is minus 8y, and this is equal to 26 plus 42, which gives us, that's 68, and we've got minus 12x. Let me just write this on the side. Okay, so we want to replace this y with negative 2/3 x minus 2. So if we substitute, this becomes negative 8 times our negative 2/3 x minus 2, and this is equal to 68 minus 12x. So let's expand here. There's negative 8 times negative 2/3 x, so that will be positive 16/3 x. Then we've got negative 8 times negative 2, which is positive 16. This is equal to 68 minus 12x. Let's put all the terms in x on one side, so that we've got 16/3 x plus 12x is equal to 68 minus 16. And let's add our like terms. So 16 over 3 plus 12, that gives us 52 over 3x is equal to 68 minus 16, which is 52. And let's multiply both sides by 3 over 52. And we get that x is equal to 3. Now that we know what x is, we can find our y using this equation here. So y is equal to negative 2/3 x, which is 3, minus 2. So if you punch that into the calculator, well, that's just negative 2, so negative 4. So we get that therefore our z, we said z is in the form x plus iy. And our x is 3, so it's 3. Y is negative 4, so 3 minus 4i. This would be our final answer. Number 7. Let f of x equal 2x squared plus 5x plus 9 over 1 minus x times 3 plus x squared. Part A. express f of x in partial fractions. Okay, so we've been given 2x squared plus 5x plus 9, and this is over 1 minus x times 3 plus x squared. So this here is a linear factor, so we can write it as a over 1 minus x plus, this is a quadratic factor. Be careful here, because if it was a repeated factor, you would have the 2 being outside. But because the 2 is inside the bracket, this is of the form ax squared plus bx plus c. So it is a quadratic. Alright, so it means since it's a quadratic, this is going to be bx plus c over our 3 plus x squared. Now let's multiply through by 1 minus x times 3 plus x squared to get rid of all of our denominators. So we get 2x squared plus 5x plus 9 is equal to a times 3 plus x squared plus bx plus c times 1 minus x. And for status, we could say let x equal 1, because I know that that would make this bracket 0. So it would make this term here equal to 0, allowing us to evaluate a. So if x is 1, that's 2 times 1 squared plus 5 times 1 plus 9 is equal to a times 3 plus 1 squared. And we say this term is going to be 0. So on the left, we get 2 plus 5, which is 7, plus 9, which is 16. So 16 is equal to 3 plus 1, 4 times a. So 4a, divide both sides by 4, you get that a is 4. And then to evaluate c, we can say let x equal 0, because we know it will make this part 0. A, we already know that a is 4. So this would allow us to evaluate c. So let's do that. Let x equal 0. So that becomes on the left 2 times 0 plus 5 times 0 plus 9 is equal to a, which we evaluated to be 4, times 3 plus 0 squared plus b times 0, so just 0 here, plus c. Okay, so c times 1 minus 0, so c times 1. So what we have is 9 is equal to 12 plus c. So c is equal to 9 minus 12, which is minus 3. And now we can use x is 2 to evaluate b, because we now have both a and c. So we can say 2 times 2 squared plus 5 times 2 plus 9 is equal to, that's a, which we found to be 4 here, times 3 plus 2 squared, 3 plus 2 squared, plus b, which is what we're looking for, times x, so times 2, plus c, which we found to be negative 3, and then 1 minus x, which we said is 2. So we need to simplify. We'll start on the left. We've got 2 times 2 squared plus 5 times 2 plus 9, and that gives us 27. And this is equal to, then we've got 3 plus 4, which is 7, times 4, which is 28, plus, here we've got 2b minus 3, and it's being multiplied by 1 minus 2, so negative 1. So 27 is equal to 28 minus 2b plus 3, because minus 3 times minus 1. So we end up with 2b is equal to 28 plus 3 minus 27. So 2b is equal to, this is 31 minus 27, that's 4, divide both sides by 2. You get b is equal to 2. Alright, so now that we found a, b, and c, we can rewrite f of x in partial fractions and say that therefore f of x is equal to, it was a over 1 minus x plus bx plus c over our, what was it, 3 plus x squared. 3 plus x squared. So we found our a to be 4 right here. So 4 over 1 minus x, plus b is 2, so 2x, c is negative 3, so 2x minus 3 over 3 plus x squared. This is our f of x in its partial fractions. Part B, hence find the coefficient of x cubed and the expansion of f of x. So let me just copy down our f of x in its partial fractions. So f of x is equal to 4. And what I'm actually going to do is I want to take this denominator up to the numerator. So it becomes 1 minus x to the negative 1. And then we're going to do the same there. So we've got 2x minus 3. And we want to take this denominator up. But be careful here, there's technically brackets here, and this is all to the power of 1. So when you take it up, it's all of this, 3 plus x squared, and this is to the power negative 1. All right. And we are interested in the coefficient of x cubed. All right, so let's start by finding x cubed from the first part here, from 4 times 1 minus x to the negative 1. So I've got 4 times 1 minus x to the negative 1. And what we want to use is the formula for binomial expansion when n is rational. This can also be extended to use. This can also be used when n is a negative integer. So that formula is 1 plus x to the n. It's provided in your MF19, so you do not need to know this by head. But it's 1 plus nx plus n minus 1 over 2 factorial x squared. And we are interested in the term in x cubed. So this next part is what's of interest to us. n minus 1, n minus 2, and this is over 3 factorial multiplied by x cubed. So since we want the term in x cubed, we should focus only on this part. There's no need to expand everything else. We don't want it. They have not asked us to expand everything else. So what we can do is to say that this becomes, this is 4, and then we're going to multiply. What's our n? Our n is negative 1. So it's n minus 1 times n minus 2, and this is over 3 factorial multiplied by our x. Be careful, in this case our x is technically negative x. So negative x, and this is cubed. Okay, so this is 4, and then let's simplify that fraction. So negative 1, negative 1, negative 1, negative 1, negative 2 over 3 factorial, and this is being multiplied by negative 1 cubed. Okay, so all of this gives us, we've got in the brackets, all that remains is going to be your x cubed, because you technically have this part, this fraction part, is going to simplify to negative 6 over 6, which is just a negative 1 multiplied by, here negative 1 cubed is negative 1, negative x cubed is x cubed. So these negative 1s cancel out, and so you just end up with x cubed. So it's 4 times x cubed, so it's 4x cubed in this instance. And then now we need to expand, do the expansion here. But how you need to think about it here is that the bracket that we need to expand is this bracket. And the terms that we get from this bracket are going to have to be multiplied to this bracket. So we need to figure out the terms that we want from this bracket, that when multiplied with terms in the other bracket will give us a term in x cubed. So what I'm seeing is that we've got 2x here. If you multiply 2x by a term in x squared, you get x cubed. Okay, and alternatively, we've got negative 3, so that's a term independent of x. If you multiply a term independent of x with a term in x cubed, then you get a term in x cubed. So ideally, we want the term in x squared from that bracket and the term in x cubed from that bracket as well. Okay, but you will see from the function of x that we have, we won't be able to get x cubed. We will only be able to get x squared. So we've got 3 plus x squared minus 1. And before we can even expand or use the formula for expansion, we need to make sure that this first number is a 1. So we need to factor out that 3. So this becomes 3 times 1 plus x squared over 3. And this is all to the negative 1. So distribute the power. So 3 to the negative 1 times the bracket to the negative 1. So 3 to the negative 1 is just simply 1 over 3 times 1 plus x squared over 3. And this is to the negative 1. And the formula that we're using is going to be the same exact formula. But the key difference here is that our x is going to be this x squared over 3. So notice that our term in x squared will come from saying nx because our function of x is x squared over 3. So we can say, don't forget your 1/3, 1/3 multiplied by our n is negative 1, times our x squared over 3, which is in place of x squared over 3. Okay. And if we went on to the next term, because this is x squared, what you'd end up with is x squared over 3 squared. And this gives us a term in x to the 4, which is not what we're interested in. We said we either want both x squared and x cubed. But if we can't get x cubed, that's fine. We just take x squared. So in this case, it's not going to be possible for us to get x cubed. So we just take the x squared. All right, so let's simplify here. We've got a third times negative 1/3. So that's negative 1 over 9. And this is x squared. All right. And so we said this has to be multiplied by that 2x here to give us a term in x cubed. So let's multiply it by 2x. So what you end up with is negative 2 over 9x cubed. So we now know that from the first bracket, our term in x cubed is 4x cubed. And then from this second term, our term in x cubed is 2 over 9, negative 2 over 9x cubed. So let's just add those two together to give us the term in x cubed for f of x. So 4x cubed minus 2 over 9x cubed. So that's 4 minus 2 over 9, which gives us 34 over 9x cubed. And this means that therefore the coefficient of x cubed is 34 over 9, and that is our final answer. Number 8, part A. Show that 4 cos to the 4 theta minus 4 is identical to cos squared 2 theta plus cos 2 theta minus 3. Okay, I think here we might want to work from the right hand side moving to the left. So cos squared 2 theta plus 2 cos 2 theta minus 3. Okay. So the first identity that comes to mind is cos 2 theta is identical to, oh, there's 3 of them really. So there's going to be cos squared theta minus sine squared theta. There's 2 cos squared theta minus 1 and 1 minus 2 sine squared theta. And here, because I can tell that the expression we want to get to on the left hand side just has cos theta, even though it's raised to the power 4, we'll figure that out along the way. I want to use this middle identity here, 2 cos squared theta minus 1, because that's the only one in which we only have cos, and that seems to be the direction we have to move in. So this cos 2 theta we're going to replace with our 2 cos squared theta minus 1. And remember, cos squared 2 theta is just the same as cos 2 theta squared. So we can also apply it here. So let's do that. It's going to be 2 cos squared theta minus 1, and this is squared. And then here we've got plus 2 times cos 2 theta. So cos 2 theta is, again, we're going to use the same one, 2 cos squared theta minus 1, and this is minus 3. All right, so here let's expand. First, Square the 2 cos squared theta, so square the 2, that's 4. Square the cos squared, that's cos to the 4. And then 2 times 2 cos squared, that's 4, times minus 1, so minus 4 cos squared. And then square the negative 1, so that's yes plus 1. And then here we've got plus 2 times 2 cos squared theta, that's going to be 4 cos squared theta. And then 2 times minus 1, that's minus 2, and this is minus 3. So what we have is 4 cos to the 4 theta, and then minus 4 cos squared cancels out with positive 4 cos squared. Then we've got 1 minus 2, which is minus 1, minus 3, so minus 4. And we have proved that therefore 4 cos to the 4 theta minus 4 is identical to cos squared 2 theta plus 2 cos 2 theta minus 3. Alright. Part B, hence find the exact value of the integral from negative a quarter pi to a quarter pi of 4 cos to the 4 theta minus 4 with respect to theta. Cos to the 4 theta would be a nightmare to integrate, so we would rather use the other side of our identity. So instead of integrating 4 cos to the 4 theta minus 4, we would rather integrate cos squared 2 theta plus 2 cos 2 theta minus 3, because we know how to integrate most of what we have here on the right hand side. So we're going to rewrite this as the integral from negative a quarter pi to a quarter pi of, that is, cos squared 2 theta cos squared 2 theta plus 2 cos 2 theta minus 3 with respect to theta. So 2 cos 2 theta, we know how to integrate that. Negative 3, we know how to integrate that. The only problem is our cos squared 2 theta here. To integrate cos squared 2 theta, we can use an identity. So the identity that we want to use to rewrite our cos squared 2 theta is going to stem from the identity cos 2 theta is identical to 2 cos squared theta minus 1. Now, what you should understand is that this is a double angle formula. And the essence of a double angle formula is that the angle on the left should be double the angle on the right. So it means that I can write a double angle formula for any angle that I want. So for example, I could say cos theta must be identical to 2 cos squared of half theta minus 1, because the angle on the left is still double the angle on the right, because half theta times 2 is just theta. Okay, so we could even go on to say, for example, cos 4 theta is identical to 2 cos squared 2 theta minus 1, because 2 theta multiplied by 2 is 4 theta. And turns out that this identity that I've just written here is what we need to be able to rewrite our cos squared 2 theta. We know how to integrate cos 4 theta. So if we can rewrite our cos squared 2 theta in terms of cos 4 theta, then that will be good for us. So let's do that. So we can say 2 cos squared 2 theta is equal to, that's going to be 1 plus cos 4 theta, divide through by 2. So you get cos squared 2 theta is equal to half plus half cos 4 theta. Alright, so we can replace our cos squared 2 theta here with half plus half cos 4 theta. So this becomes the integral from negative a quarter pi to a quarter pi of, that's going to be cos squared 2 theta, so that's half plus half cos 4 theta plus our 2 cos theta minus 3, 2 cos 2 theta minus 3. And this is all with respect to theta. Now we can go ahead and integrate. In fact, we've got like terms. We've got half minus 3, Half minus 3 is what? That's minus 5 over 2. All right. So I'm just going to remove this here so that we've got minus 5 over 2 at the beginning here. So that's going to be minus 5 over 2. So if you integrate minus 5 over 2, it's going to become minus 5 over 2 theta. And then if you integrate here, we've got half cos 4 theta, so it's going to be plus half. If you integrate cos, you get sine. So we've got sine 4 theta. And if you differentiate 4 theta, you get 4. So it means we're going to have to divide by 4. I'll just write it as times a quarter. Okay, and then let's integrate 2 cos 2 theta. So that's 2. If you integrate cos, you're going to get sine, so sine 2 theta. Differentiate 2 theta, you get 2, so let's divide by 2. Okay, and we're going from negative a quarter pi to a quarter pi. Negative a quarter pi to a quarter pi. Let's simplify our result. So this is negative 5 over 2 theta. Then we've got plus 1 over 8 sine 4 theta. And then the 2's here would cancel out. So it's plus sine 2 theta. And we're going from negative a quarter pi to a quarter pi. And we can go ahead and substitute in our limits. We can start off with our upper limit. So that's going to be negative 5 over 2 times a quarter pi plus 1 over 8 sine 4 times a quarter pi, so that's just going to be sine pi, plus sine 2 times a quarter pi, so 1 over 2 pi, minus, let's do our lower limit now, so that's minus 5 over 2 times negative a quarter pi, plus 1 over 8 sine 4 times negative a quarter pi, so that's negative pi. And then we've got plus sine 2 times negative a quarter pi, so negative 1 over 2 pi. Now let's simplify starting here. So that's negative 5 over 2 times a quarter. So that's going to be negative 5 over 8 pi. And here we've got sine pi. Sine pi is going to be 0. And then we've got sine pi over 2, which is plus 1, minus our lower limit. We've got minus 5 over 2 times minus a quarter pi. So that's positive 5 over 8 pi. And then here we've got 1 over 8 sine negative pi. Sine negative pi is 0. Then we've got sine negative half pi, which is negative 1. And so we've got negative 5 over 8 pi plus 1 minus 5 over 8 pi minus minus 1, so plus 1. So we end up with 2 minus 5 plus 5, so that's 10 over 8 pi. And if we simplify the 10 over 8, that is 5 over 4. So therefore this is 2 minus 5 over 4 pi, and that is our final answer. Number 9. Relative to the origin, all the points A, C, and D have position vectors given by OA is I plus 6j plus 3k, and OC is 7i plus 3j plus k, and OD is 3i plus 2j plus k. A fourth point, B, is such that ABCD is a parallelogram. Part A. Find the position vector of B and verify that the parallelogram is not a rhombus. Alright, so a parallelogram looks like this. Our opposite sides are going to be equal. And they are going to be parallel. So this side is parallel to that, and then this side is parallel to this side. Now, a rhombus would have all four sides being equal, so it would also be parallel, right? but we're saying this side would be equal to this side, which would be equal to that side, and that's equal to this side. So it would have the same traits of parallelism, but all four sides would also be equal. So if we want to prove that our parallelogram is not a rhombus, we just have to show that this side is not equal to this side. Because otherwise, if they're equal, it would be a rhombus. Okay. So we are given what? A, B, C, D. We need to first find the position vector of B. Alright, the way we can do that is looking at our diagram here. The vector AB, right, going this way, should be the same as the vector DC. So AB should be the same as DC. Okay. And we can rewrite our displacement vectors in terms of their position vectors. So AB is the same as OB minus OA. And then DC is the same as OC minus OD. And what we're interested in is OB, so I'll just make that subject of the formula. So OB is equal to OA plus OC minus OD. And we have OA, we have OC, we have OD. So we can simply substitute. So OB is equal to, our OA is I plus 6J plus 3K. Then our OC is 7I plus 3J plus 4K. So 7I plus 3J plus 4K minus our OD, which is 3I plus 2J plus K. All right, so OB is equal to, we've got I plus 7I, so 8I, we've got 6J plus 3J, so 9J, and then 3K plus 4K, that's 7K, minus, let's expand here, so minus 3I, minus 2J, and minus K. So it means that therefore OB is going to be equal to, that's 8I minus 3I, 5I, 9J minus 2J, that's 7J, and then 7K minus K, that's positive 6K. Perfect. All right, so that's the first part of the problem done. We have found the position vector of B. Now we need to verify that the parallelogram is not a rhombus. So like I said, we just have to show that AB, the length of AB, is not the same as the length of BC. So magnitude of AB is not the same as the magnitude of BC. So this is what we need to prove. But instead of using these two sides, or because I have knowledge of the next question, we're going to want to find angle BAD. I am going to choose to use I'm going to choose to check that AB is not equal to AD, because remember AD and BC would be the same. So I could either use BC or AD. It would be the same argument. So I just have to prove that these two adjacent sides are not equal to each other. So what we need to prove is that the magnitude of AB is not equal to the magnitude of AD. If it is equal, it means we've got a rhombus. So to be able to do that, we first need to find the actual vectors of AB and AD. So AB, like we mentioned earlier, is OB minus OA. So AB is equal to, our OB is 5I plus 7J plus 6K minus our OA. Our OA is negative, so that's going to be minus I minus 6J minus 3K, minus 6J minus 3K. So AB is equal to 5I minus I, 4I, 7J minus 6J, J, 6K minus 3K, 3K. We now have AB. And we can go ahead and find its magnitude. The magnitude of AB is going to be the square root of 4 squared plus 1 squared plus 3 squared. So the magnitude of AB is equal to, as 16 plus 1, 17 plus 9, so root 26. And I don't think that simplifies. No, it does not. Root 26. And we're going to do the same for AD so that we can show that the magnitude of AB is not the same as the magnitude of AD. So AD is going to be equal to OD minus OA. So AD is, what is our OD? OD is 3i plus 2j plus k, 3i plus 2j plus k, and minus OA is this expression over here, minus I minus 6j minus 3k. So it means our AD is equal to 3i minus I, 2i, 2j minus 6j minus 4j, k minus 3k minus 2k. Alright, now let's find its magnitude. So that's going to be the square root of 2 squared plus negative 4 squared plus negative 2 squared. And if we punch this into the calculator, oh, we can do it manually because why not? So that's 4 plus 16, which is 20, plus 4, so 24. So this is the square root of 24, which is 4 times 6. So 2 root 6. Square root of 24, yes, it is 2 root 6. Alright, so clearly they are not equal. If you really wanted to make this even clearer, you could give approximate values here. This is 4.899, and then root 26 is going to be 5.099. So clearly our 5.099 is not equal to 4.899. So magnitude of AB is not equal to the magnitude of AD. Hence, it is not a rhombus. It is not a rhombus. And that would be our final answer. Now, part B says, find the angle BAD giving your answers in degrees. Coming back to our diagram here, the angle that we want is going to be this angle over here. That's angle BAD. And remember, if we want to find the angle between two vectors, you have to pick two vectors that are either going towards that angle or away from that angle. They can't be going in different directions. So you could either pick BA and DA because those would be both going towards our angle. Or alternatively, you could pick AB and AD because those are both going away from our angle. And I hope you understand why I chose to use AB and AD in our earlier question, so that we wouldn't have to recalculate them in part B because we already found them in A. So the formula we use for angle between two vectors is cos theta is equal to AB, where A and B are the vectors, magnitude of A times magnitude of B, where A and B are vectors. So in our case, A and B are going to be our AB and AD. So in other words, what we have is cos theta is equal to the dot product of AB and AD divided by the magnitude of AB times the magnitude of AD. Magnitudes of AB and AD we already found. We've got root 26 and 2 root 6. The only thing we need to find is the dot product of AB and AD. So let's do that. AB dot AD. What was our vector AB? AB is 4I plus j plus 3k. I'm just going to rewrite that as a column vector so that it's clear. 413 dot, and I'll do the same for AD. AD is 2I minus 4j minus 2k. So 2 minus 4 minus 2. Okay, so that's going to be 4 times 2, which is 8. 1 times negative 4 minus 4. 3 times negative 2 minus 6. And so that's 8 minus 10, which gives us minus 2. Okay, so it means our scalar product or our dot product is negative 2. So we've got cos theta is equal to negative 2 over the products of their magnitudes. So the magnitude of AB is root 26 and that of AD is 2 root 6. So it's gonna be divided by root 26 times 2 root 6. And so theta is going to be arc cos of all of this. Arc cos of 2 over root 26 times 2 root 6, and theta is equal to, we are in degrees, so that is arc cos of 2 over, I omitted the negative 2 there, it should be negative 2. So arc cos of negative 2 over the square root of 26 times 2 root 6, and this gives us 94.6 degrees, correct to 1 decimal place. Alright, and then part C says, find the area of the parallelogram correct to 3 significant figures. So the area for our parallelogram is just going to be our AB, the magnitude of AB, times the magnitude of AD, times sine of the angle that's in between those two lines. So times sine of BAD, which we found in part B. So this is our formula for area of parallelogram. And we've already evaluated these magnitudes as well. The angle we already have, so we have everything we need. So we're saying it's the magnitude of AB times the magnitude of AD times sine of our angle BAD. So the magnitude of AB, so that's root 26 times 2 root 6. Root 26 times 2 root 6 times sine. And for the angle here, I'm just going to rewrite, this is the final answer, I'm just going to rewrite the angle with more decimal places so that we don't get rounding errors when we substitute here. So 59225, I think that should work well. So 94.59225. So if you notice that your final answer should be to 3 significant figures, make sure that you're either working with exact values in your calculation, or make sure that you're always working with more than 3 significant figures in your calculation. Alright, so let's punch this into the calculator. This is root 26 times 2 root 6 times, this is sine 94.59225, which gives us, that is 24.9. And this is going to be our final answer to 3 significant figures. Number 10. A container in the shape of a cuboid has a rectangular base of length 2x and width x. It has a height of 4 minus x. It is given that x varies with time t, where t is greater than 0. The container decreases in volume at a rate which is inversely proportional to t minus a quarter. When t is equal to 1 over 2, x is equal to 2, and the rate of decrease of x is negative 4. Part A. Show that x and t satisfy the differential equation dx dt is equal to 32 over 4t minus 1 times 16x minus 6x squared. There's a lot that's going on here. Okay, so maybe the first place to start is a container in the shape of a cuboid has rectangular base of length 2x, width x, and height 4 minus x. So if we wonder the volume of our cuboid, it's length times width times height. So it's going to be 2x times x times 4 minus x, which is the height. So the volume is equal to, that's 2x squared times 4 minus x, which we can simplify further to 8x squared minus 2x cubed. Okay, so that's the first line. Now we're given that x varies with time t where t is greater than 0. Okay, then we're given that the container decreases in volume at a rate. So the volume is changing at some rate. So that's going to be dv dt. This is volume changing with respect to time. Okay, and we're told that this is inversely proportional to t minus a quarter. So we're looking at 1 over t minus a quarter. But also take note that they say decreases. So this is actually negative. Okay, and so if we get rid of the proportionality sign and we move to an equal sign, we get our constant of proportionality, and this is t minus a quarter. Then here we're given that when t is half, x is 2, and the rate of decrease of x, so that's dx dt, is negative 4, so dx dt is negative 4. Okay, and we need to find dx dt. So we can create a chain rule to find dx dt, and what we can do, we need a rate that has dx, so we can get that from differentiating here. If we differentiate here, we get dv dx, which is going to be 16x minus 6x squared. All right. And notice that here we want dx in the numerator. So it means that we're going to have to flip this dv dx so that we get dx dv. What you do on one side, you do on the other. So this is 1 over 16x minus 6x squared. All right. And so we can write that dx dt is equal to dx dv multiplied by dv dt, dv dt. All right. And then the dv's technically can cancel out so that you've got dx dt. So our chain rule is valid. Okay, perfect. So now let's just simply substitute to get dx dt. Dx dt is dx dv, which we said is 1 over 16x minus 6x squared. And this is being multiplied by dv dt, which is negative k over t minus a quarter. Okay. And so dx dt is equal to, this is 1, or not 1, but negative k over t minus a quarter multiplied by 16x minus 6x squared. All right, and we need to find what k is. We've been given t, x, and dx dt, so we can do that. So dx dt is negative 4, and this is equal to negative k over, t is going to be 1 over 2, and x is 2. So 1 over 2 minus a quarter times 16 times x, which is 2, minus 6 times 2 squared. Okay, so we've got negative 4 is equal to negative k. Let me punch the denominator into the calculator. So that's half minus a quarter times 16 times 2 minus 6 times 2 squared, and this gives us, we're dividing by 2 here. So this would mean that therefore k is going to be equal to a positive 8. So what we have is that dx dt is equal to positive 8 over t minus a quarter times 16x minus 6x squared. All right, and let's see, what do they have? So this is not quite it. They've got 32 in the numerator, but also notice that this is 4t minus 1 instead of t minus a quarter. So this looks like they have factored out the quarter in the denominator. So it would become, in fact, let's just work on it on the side. We've got t minus a quarter, right? And we can factor out a quarter. And so this becomes what? 4t minus 1. Because a quarter times 4t gives us t. A quarter times negative 1 gives us negative a quarter. And so what ends up happening is that you've got dx dt is equal to 8 divided by our quarter times 4t minus 1 times 16x minus 6x squared. All right, so this just becomes dx dt is 8 times 4 over 4t minus 1 times 16x minus 6x squared. And so therefore dx dt is equal to 32 over 4t minus 1 times 16x minus 6x squared. And this is going to be our final answer. It matches exactly what they are looking for. Part B then says solve the differential equation obtaining an expression for t in terms of x. Alright, so we are solving the differential equation dx dt is equal to 32 divided by, that's 4t minus 1 multiplied by 16x minus 6x squared. Alright, so the first step when solving your differential equation is to separate your variables. So we want to move everything that is x to the left and everything that is t to the right. In this case, everything that has t is already on the right hand side. So we need to move this bracket with x to the left so that it becomes 16x minus 6x squared with respect to x is 32 over 4t minus 1. And then we're just going to move the t to the right hand side. So dt. Once we've separated our variables, we can go ahead and integrate both sides. So we'll start with the left. If you integrate 16x, you get 16x squared over 2 minus, if you integrate negative 6x squared, that's negative 6x cubed over 3 plus a constant of integration. And then here it's going to be 32 ln 4t minus 1. But remember, we have to differentiate our 4t minus 1. So if you differentiate 4t, what do you get? You get a 4. So divide by 4. So at the end, we've got 16 over 2, which is 8x squared, minus 6 over 3, so minus 2x cubed, plus our constant, 32 over 4 is 8, so 8 ln 4t minus 1. And they want the answer in terms of t and x, so we need to evaluate our constant here. We have enough information, I believe. Yes, they told us that when t is half, x is 2. So we can substitute. We know that when t is half, x is 2. So substitute this x with 2 and then substitute t with half. So it becomes 8 times 2 squared minus 2 times 2 cubed plus c is equal to 8 ln 4 times 1 over 2 minus 1. Alright, so let's simplify. I'm going to punch this into the calculator. That is 8 times 2 squared minus 2 times 2 cubed, which is 16, plus our constant, is equal to, that's 8 ln, that's going to be 4 times half, so 2, 2 minus 1, 1. Alright, so 16 plus c is, ln 1 is 0, So we get that C is negative 16. So as a result, our solution is going to be, we're looking here, it's going to be 8x squared minus 2x cubed plus C, which is minus 16, is equal to 8 ln 4t minus 1. I believe they specified how they want it. Yes, they want t in terms of x. So we need to make t subject of the formula. So what this means is that we've got, so we can divide through by 8. So if we divide 8x squared by 8, it's x squared. Divide negative 2x cubed, that's negative 1 over 4x cubed. Divide negative 16 by 8, that's negative 2. And this is ln 4t minus 1. Just going to rearrange this ln 4t minus 1. I want to rewrite this in order of descending powers. So negative 4x cubed plus x squared minus 2. Okay. And now let's apply the exponential function on both sides to get rid of this ln, so that we end up with 4t minus 1 is equal to the exponential of, that's negative 1 over 4 x cubed plus x squared minus 2. If you haven't seen this notation before, it's the same as e of x is the same as the exponential of x. Okay, it just makes it easier to write when you've got longer powers, longer indices. All right, so we've got 4t minus 1 is equal to that. So add 1 to both sides, you get 4t is equal to 1 plus our exponential of negative a quarter x cubed plus x squared minus 2, and then divide both sides by 4, so you get t is a quarter plus a quarter exponential of negative a quarter x cubed plus x squared minus 2, and this would be our final answer. Okay, and it also seems like that's it for the guess paper. Alright, I wish you guys the very best in your final exams for Pure 3. And if you did find this useful, please make sure to share it with as many people as you know who are writing. Stop trying to pass alone. Let's make sure that everyone passes, even though it might mean that our threshold would be higher. Sharing is caring. All the best in your exams. Good luck. Bye bye.